For chip-level verification, the MiM-generated models can be used as is in most chip-level verification flows. Whether chip-level verification is driven by the analog or digital verification team, if all you need are the models, then you're all set. There is some code that can be added to your test bench to make the most out of our models, but you can refer to our documentation or look at any of our MiM-generated test benches and copy a few lines of code. In this video, we're going to show you how to use MiM to verify the analog system in the context of the top-level schematics. We'll be looking for incompatibilities between otherwise functional blocks and wiring errors in the top-level schematics. We're going to create a single model for the entire analog system, which is sometimes needed in your chip-level verification flow. We're going to show one way in which MiM assists in bringing up a chip-level simulation, and finally, we're going to show you how we tie everything together, both block-level verification and the system-level verification we're showing here. The starting point for this video is that you have a snapshot of the top-level schematics ready and that you have verified models in the cadence hierarchy. Here, I have the Cadence Library Manager open. For one of our blocks, the bias block, you can see the various views that are already here. The MiM view is the Verilog AMS model, the schematic is here, the specifications are here, a PDF version of the specifications are here, and the symbol is here. The buck, however, which is at a higher level, and the advanced buck, which is also at a higher level, only the schematics are currently available. Let's go ahead and open the schematic for the advanced buck. Here you'll see the various blocks of the buck regulator. Let's zoom in a little bit to take a look. This buck takes as inputs differential digital signals. So here's a buffer to convert it to a single-ended input, and these buffers are here for both the control bits and the enable line. We have a reference generator here, an op-amp, a comparator, our gate drivers, we have our pulse width modulator, and we have a bias generator. And up here we have an overcurrent detector. In addition, we add an analog test bus. The control inputs are here for that, and the multiplexer for the analog test bus is here. Now let's go back to our MiM specifications. Let's go ahead and take a look at the one for the advanced buck. Here you can see we provide information for the behavior and we provide information for the test bench. Now again, I can use the block level models as is. What I'm showing you here is not necessary if all you want to do is to use your block level models with your chip level test bench. However, if you want a single model of your analog system and you want to verify that that model is correct, here's how you can do it. We go ahead and enter the behavior of the analog block as shown here. We can enter ranges for assertions as well. And we enter the information needed to create a test bench. So far I've done nothing differently than what I did before. At this buck system level, I followed the same procedure that I did for the ADC, DAC, and LDO and the other examples by just providing the behavior and the information needed for the test bench. In fact, all I need to do is to hit generate in view, and I can generate the model in the test bench. So if I want to see what the test bench looked like, either as a template for a test bench or for the additional code that I can add to my custom test bench, I can just hit view here and I can take a look at the code for the test bench. Let's talk about how I'm going to verify this model. Normally what we do at the block level, when we do a block level model versus schematic comparison, is that we apply the same stimulus for the block to both the model and the schematic. We go ahead and compare the outputs. And this is done for each of the blocks. At the system level, we're going to do something similar. We're going to apply the system level stimulus to the top level model, but this time instead of applying it to the schematic, where every view is a schematic, we're going to apply it to the top level schematic, where the views are the models. We'll go ahead and compare the outputs, and if they're the same, within some tolerance, we'll say that the top level model and the top level schematic, or the schematic of models, are functionally equivalent. And so we're applying the principle of hierarchical verification here. We could simulate the top-level schematic with schematic views, but the simulation will likely be too slow. So the idea here is that we still have traceability to the transistors. These models have been verified against the schematic, and now we're going to simulate using those models in the top-level schematic, and we're going to do a comparison with the top-level model, and therefore we have traceability from the top-level model to the schematics at the device level. Let's go ahead and try to accomplish this task. I go back to the specification lists page, I select manage, and now I'm going to include the buck and the advanced buck to be managed. I hit update, and now those will be managed as well. And you can see that here on the summary page. You can see that on the row with the buck, you can see download, publish, and the config views are available. Same is true with the advanced buck. Now I'm going to go back to my Unix window, bring up the clock like I did before, and type auto MIM manage. What this will do is everything we did before in the block level verification video. And in addition to that, it'll generate the models for the buck and the advanced buck. It'll publish them into the cadence hierarchy and will run this hierarchical simulation. And as before, this will take some time, so I'm going to speed up this segment of the video. You can now see that instead of 14 blocks in the repository, there are 16. So the two additional ones are the buck and the advanced buck. If you take a look at the directories present, you'll now see the buck and the advanced buck. Let's go into the advanced buck directory and take a look. Now if we bring up the hierarchy editor, we can see the configuration that was being simulated. We can use the avhed command for that. The test bench instantiates both the model and the schematic. So for the advanced buck, which is being instantiated, the test bench instantiates both the MIM view, which is the model, and the schematic view. The test bench is a MIM view, and then for the blocks, bias, clamp, comparator, gate drivers, and so on, the MIM views are being instantiated, which are the models. So we are comparing the top-level model of the buck with the schematic of models. In this directory, we can also see all of the generated views. What's pushed in the cadence library is what's in the local directory. Here, we can see the library, the cell, and the view of what's being pushed in. So here's the top-level model for the advanced buck. Here's the specification. Here's the PDF of the specification. Here's the code for the test bench. And here are the two configurations, one for model versus schematic and one for model versus model. So if you want to use the test bench as a template, this is where you can look. To look at the simulation results, I can again use the AV command. At the top level, I'm adjusting the control for the reference, and I'm adjusting enable. I can look at the output for the schematic of models, and I can look at the output for the model. I can plot when tests are run and when they're failures. You can see how the model of the buck exhibits idealized behavior, while the schematic of models exhibits non-ideal behavior such as settling. For the purposes of making comparisons between the model and the schematic, we take samples. The test signal indicates where those samples are taken. We take into account the non-ideal behavior in the schematics by not sampling until after the signal is settled. To show how we can use the system in debugging a problem, I'm going to purposely create an issue. Recall that many of our blocks, such as the ramp generator, have a current input. In particular, the ramp generator has a minus 250 nanoamp bias current, with a range of minus 275 nanoamps to minus 225 nanoamps. I'm going to go ahead and change the bias. So rather than have 250 nanoamps, I'm going to have 280 nanoamps, which would be out of range. Again, you can see that I've now changed the bias. I'm now going to go back and run a simulation. We can see the failures as expected. In the bias, there was one failure. It's due to the model versus schematic failure. We adjusted the bias current in the bias MIM specification or in the model, but the schematic was not changed. So there was a mismatch in the bias between the model and the schematic, and that resulted in the one failure. In the buck and the advanced buck, in the current source from the bias of the ramp generator received the wrong current and issued a fault as a result. So while we can't know exactly how many times the fault would be triggered, we do see that there are faults in the buck and the advanced buck simulations. We'll be looking at the text output and the waveforms to examine these faults in detail. So in the simulation summary, we now see the three failures. We see it in the bias, the buck, and the advanced buck. And in the summary, we see the number of failures. In this case, we see an error in the bias block due to the inconsistency between the model and the schematic. However, there could have been a situation where there was a human communication error during the design of the bias block as to what the current to the ramp generator should be. The bias model and the schematic would have been designed to produce the same wrong output current, and the block level verification would have passed. This design error still would have been caught during a system or chip level simulation with the models. Suppose we didn't know where the fault came from in the advanced buck. There are multiple ways to try to track down the fault. The first one is just to look at the simulation summary. Here immediately, you can see that a fault was detected at 1 microseconds. It was in the buck advanced test bench, in the device under test, which is the schematic view, the RG instance, which is the ramp generator, indicating that the I bias was out of range. The subsequent failures are probably due to the fact that when the ramp generator specification or model detects the bias out of range, the output is shut down to make it obvious that something is wrong. So if the ramp generator is shut down, then the advanced buck won't work, and therefore the output voltage from the buck converter will not be correct, as shown in these failures. In all of the blocks, we gated the range or the assertion test with the enable. As a result, when enable equals 0, we don't get any issues. But when we turn enable back on, we now see a fault again. We can also use the waveform tool to figure out where the fault is. As before, we'll plot some relevant signals. Control, the enable, the output for the schematic, the output for the reference, where the tests are, where the failures are, and we'll also plot the fault variable, and we'll plot something called the fault message variable. Here, we'll go ahead and look at the overall waveforms. When we look at the fault variable, we can see here when the fault variable is high. So there's a fault here. The fault drops to 0 because this is when the enable line drops to 0. The fault becomes a 1 again when enable becomes a 1. What this fault message allows us to do is allows us to see where the fault is. If I right click on this and I change the ASCII, in the waveform viewer, I can see where the fault lies. The fault lies in the advanced buck test bench, in the device under test, which is the schematic view, and the RG instance, which is the ramp generator. Now if I expand this, I look at the device under test, I look at the RG block. Within this RG block, I also have a fault variable. This is the fault variable local to the RG block, or the ramp generator block. I can see a fault. If I actually want to see a plot of the failure, I can expand the RG, plot underscore faults. I'll see my 3 fault variables, one for bias, one for VDD, and one for VSS. There's one corresponding to each of the assertions that I have, or each of the places where I filled in the range column, and you can see that the fault lies within I-bias. I can of course plot the current, I underscore bias. I can see that the bias is minus 280 nanoamps, which is out of the range of minus 275 nanoamps to minus 225 nanoamps. So very quickly, using the waveform tool, I can also figure out where the fault occurs. It can often take days to get a chip level simulation going. And one of the reasons it can often take days is that the setup isn't quite right. There's an incorrect bias somewhere, there's an incorrect voltage reference somewhere. There could be hundreds of bias lines and tens to hundreds of voltage reference lines. By being able to quickly isolate where the faults are, we can quickly debug our system to make sure the setup is correct as far as bias lines and supply lines go. Let's now go ahead and undo that change and get everything back to working again. As before, I'm going to use the revision control system to undo that change. You can see that we've reverted back to the previous version. I'm now going to run the simulation again. As expected, all of the test benches ran without any errors. Using this approach, we can complete analog block and system level verification at any time during the design process. With a single command, we can detect if there are any changes, whether in the schematic, MiM specifications, PDKs, EDA tool versions, anything that might cause a functional error. Thank you for watching. Please click in the upper left for our next video. Please click in the lower left for the playlist of all of our videos in this series. Please click on the right to subscribe to our channel.